Thank you very much.
Okay, so we all know that cancer is dangerous, but what it makes it truly life-threatening is when it spreads to other parts of the body. The cells in this process, it's called metastasis, and the cells have to survive in completely different environments. First, they have to escape from the primary tumor, enter into the circulation, travel through it, exit from the circulation, and try to seed and growth in a new organ. And this process is quite inefficient, actually, and not all cancer cells are able to do that, luckily. Only few manage to complete all this journey, and the key trait that allows them to succeed is called plasticity, which is the ability of the cells to adapt and survive in changes and different pressures. To understand this better, think about Squid Game, which I hope you have seen it, which is a survival show in which hundreds of people, all in depth, compete in deadly challenges to win a huge prize. At the beginning of the game, they're all the same, they're all poor, but as the game progresses, all the difference emerges because some of them build alliances, others manipulate the others. But only the one with the right mix of traits will be able to survive and win the game. And this is more or less what's happened inside a tumor, because at a first glance, not all cancer cells are the same. A tumor is made up by different types of cells, and this is called tumor heterogeneity, and it can exist at many levels between patients, between tumors, and even within a single tumor. And the more heterogeneous a tumor is, the harder it is to treat it because it contains different player types, and some of them could be master at surviving. That's why in our research we go beyond looking at the tumor as a whole. We zoom in at the single cell levels so we don't miss out the few cells that are truly dangerous, because our goal is to look for those highest plastic cells that are most likely able to escape from the primary tumor, resist therapy, and form the metastasis. So what we do, we mimic the pressure, mechanical pressure that the cell experiences during all the journey of the metastasis process, and we squeeze them in a very restricted space, in this case 3 micrometers, and we observe them under the microscope, and we analyze their characteristic with artificial intelligence. And we use AI because it's able to detect subtle differences that would be impossible to catch just by our eyes. So we look at them, we look at their shape, we look at the movement, how they adapt under this pressure that we are applying, and we, with all of these characteristics, we extract and we create a profile of the most dangerous cells based on the features that we have extracted with our analysis. And by doing that, we create this profile of the most dangerous cells that we are coined as the plasticity score, which is now a tool that is able to rank the cells from the least to the most plastic. And of course, the more plastic a cell is, the more aggressive it becomes and would be difficult to stop it, basically. So our goal now is to translate these plasticity scores into reality with patient samples, of course, and searching for those high-risk traits in the patient. So this will give us the opportunity to identify high-risk patients early and be able to stop the aggressive cell before they spread, and eventually be also able to improve the treatment of cancers. So thank you very much.